Any questions about any of the initial condition stuff, especially about signs? Oh, Dom, somehow I skipped over you.
Yes, sir.
Don't worry, you'll be next.
Yes, sir.
So I just want to give you an honest pause to see if you've got questions about any of this. Okay, well, let's do the next section.
So here we'd draw for time greater than 0, so we can find our omega naught as well as our alpha, and then our S, right?
That's exactly right.
And
what
so
is that? And what is that called when we're drawing?
finding the natural solution.
That's it.
And so just a quick question, 2 questions. Actually, never mind, 1 question. We can, for redrawing this, can we just, that most recent diagram you drew, but since it's time greater than 0, not 0 plus, just replace the 6 amp source with the inductor and then the source with just the capacitor. And then can we just keep that like that, right?
That is it exactly.
Okay.
So the next, can everybody see this upper right-hand corner?
Yes, sir. I think so.
I'm never sure. Sometimes my screen does not match exactly what you see. So our next step is to find out that natural solution. And to draw that, we'll draw it for t greater than 0. And when we draw it, we'll have, just like Dom said, we'll have our resistance. And we can really just draw these resistances all lumped together, because for time greater than 0, everything's in parallel, everything's in series. And it becomes just this by the same reasoning we did for t greater than 0, just as Dom said. So we do need, though, to be careful about drawing in our parts. We've got to draw our IC coming down here, and that's about it. Okay, so the first question is, Dom, I'm going to let you continue. What formula will you use for alpha?
So for alpha,
yeah.
So would you use the series one, the R over 2L?
That's right.
Okay. And then the omega naught just has 1, which is the 1 over square root of R, square root of LC.
Right? That's right. So okay. For this, it just tends, it's the series. And for this, omega sub naught is always, no matter if it's series or parallel, this, which for this particular circuit turns out to be the square root of 75. You can simplify that into 5 times the square root of 5. I think this is just faster. And so now the question is, which is bigger, alpha or omega naught?
Alpha.
Alpha is bigger, yeah. This should have to be the square root of 100 for them to be equal. So now that we've got that,
would that mean that it's now overdamped?
It is overdamped, which is nice if you don't like oscillating functions. Now you figure out what your values of S are, and that is always going to be, whether or not it's in series or parallel, it's going to be that equation, which is -5 and -15. So our natural solution is going to look like C1 e to the minus 5t plus C2 e to the minus 15t. All right, is that what we want to highlight as our natural solution, or do we need to firstly use those initial conditions we just so painfully found to solve for our C1s and C2? Sabine, which of those answers is correct?
So you would want to solve for C1 and C2 using your initial conditions, but you need to find the forced solution before you can do that.
That's exactly right. So that's exactly right. So your natural solution is done right here with those unknowns. Keep those unknowns right there. And then our next step, as Sabine said, is to find that force solution. And Sabine, just continuing on with you for a moment, what time is that?
That is time equals infinity. So your inductors are going to be shorts and your capacitors are going to be opens.
That's right. Now, you could draw that, but can you see how there's no
It would
can you
just be zero.
there's nothing forcing it there at that point. You've taken out your source. So just by inspection, your VF will be 0. And now, Aiden, what's the formula for your total?
It would just be your natural solution.
That's right. In general, it's your natural solution plus your forced. But since your forced solution is 0, don't be misled by thinking it's always going to be equal to your natural solution. It's not. It's only your natural solution if the forced solution is 0. Okay, and now we want to find our unknowns by substituting in our initial conditions. At t equals 0, we have VC is 108. And what does that equal, Phil, in terms of our C1s and C2s?
So that's going to equal C1 plus C2.
That's it. In fact, I'm going to draw it the other way just to get into that standard form. C1 plus C2 equals 108. And then, Phil, just continuing with you, tell me what the derivative would be taken at 0.
So it's going to be, I guess, drawing it the way you want to draw it. Negative 5 C1 minus 15 C2 is equal to negative 450.
Yeah, that's right. And I kind of like the way what you said is about the way that I drew it, because what he's saying is that, hey, I see all these negatives. Why don't we just simply make them positive? Multiply through by -1. And then now they're just instantly all positives, which saves us a sign. And now you can put them in matrix form. You can say it's equal to 1 and 1, 5 and 15. We have our unknown C1 and C2 equals 108 and 450. And if you were better at algebra than I could, you could probably just divide these guys by 5 and simplify it still further. But I'd be worried about making a mistake with my math, and so I just keep it like that. Throw it in my calculator and get an answer. And when you do, it will tell you your C1 and your C2 variables. And if you're not sure how to do it in your calculator, call that matrix A, call that matrix B, and then you want to say your inverse of A times B, and it will times B, that's a times. Let me try that a little bit better. It will be your inverse of A times your B. But your calculators will probably have faster ways to solve for it rather than you creating the two matrices and then multiplying them. They probably have a simultaneous equation solver. And anyway, it will come out to be 117 and minus 9. And now you can write your entire solution as 117 e to the minus 5t minus 9 e to the minus 15t. And that's it.